You're using large language models every single day, whether you realize it or not. But have you ever stopped to wonder what's actually going on inside that digital black box? Is there a real mind in there, or is it all just a very, very clever trick? Well, let's pull back the curtain and find out.
Yeah, this really gets to the heart of the biggest misconception about AI, doesn't it? It feels so real. It feels like we're talking to a conscious entity, some kind of digital soul. But the reality, as we're about to see, is way more mechanical. And honestly, it's much more fascinating. So, if it's not a thinking machine, then what in the world is it? Well, the best place to start is to think of it as the most sophisticated autocomplete you've ever laid eyes on. You know how your phone tries to guess the next word you're going to type? Imagine that, but an autocomplete that has read pretty much the entire internet. It's a simple idea, but it is incredibly powerful.
Right. Forget about understanding or reasoning for a minute. The single, solitary goal of a large language model is to look at a bunch of text and make a really, really good guess about what should come next. It's a pattern-matching machine that has gobbled up trillions of words to get insanely good at this one guessing game. Okay, so to understand how it makes that guess, we first need to get a handle on the language it speaks. And it doesn't speak in words, not really. It speaks in something called tokens. So a token is the basic building block. Sometimes, yeah, it's a whole word, like the or and, but other times it's just a piece of a word, or maybe even just a comma. This is how the model chops up our complex, messy language into neat, tidy little chunks that it can actually do math on. And this is where you start to see just how differently the machine reads. It knows a common name like Chuck is one token, easy, but an uncommon name like Mangione, it gets chopped into pieces, Mong and Ione. See, it's not reading for meaning the way you and I do. It's just breaking our language down into a sequence of statistical Lego blocks. All right, so the model has turned our text into a nice, neat list of tokens. Now for the main event. How does it actually decide what token comes next? The whole process is actually a pretty straightforward loop. It's kind of beautiful in its simplicity. First, it looks at everything that's been written so far. Second, it calculates the odds for every single token that could possibly come next. Third, it picks one. And fourth, it just adds that new token to the end and starts the whole process over again. One token at a time. Now that right there is the billion-dollar question, isn't it? It all comes down to the patterns, the trillions of patterns it learned during its training. Let's look at a real example. Okay, so let's say we prompt the model with something simple, like, the capital of France is. The model then does its thing and calculates the probability for the very next token. And as you can see here, it is overwhelmingly confident, like 91.9% sure that the next token should be Paris. Now, why is that? It's not because it knows geography. It's because it has seen that exact pattern countless times in its training data. It's not reasoning. It's just recognizing a super common pattern. But, and this is the twist, this is really important, it doesn't always pick the number one option. To keep from being totally robotic and predictable, it samples from the list. Think of it like rolling a weighted die. Tokens with a higher probability are way more likely to get picked, but they're not a sure thing. This little bit of randomness is where all the creativity and all the errors come from. And this slide shows that randomness in action. Let's pretend the prompt was, the capital of England is. Now, based on the patterns, the model might give London a 38% chance, but it might give Paris a 29% chance because, hey, it's another big European capital, right? It's a common association. So if that weighted die just happens to land on Paris, the model spits out the wrong answer. It's a mistake for sure, but it's a statistically plausible mistake based on all the data it was fed. Now, I know calling this whole thing fancy autocomplete can feel a little, dismissive, because while the output is simple, the calculation that goes into it is anything but. And this is where the chess player analogy is so perfect. So on the surface, what you see is super simple, just one token after another. But underneath, to pick that one single token, it is performing an unbelievably complex calculation. It's looking at the relationship between every single token that came before it to figure out the absolute best next move. I mean, think about it. A grandmaster chess computer is analyzing millions, maybe billions of future possibilities. But all we see is its hand moving a single pawn. The LLM is doing the exact same thing. Its simple one token at a time output completely hides a breathtakingly complex analysis of the entire conversational board.
So once you really get this idea of probability and complexity, a lot of the weird stuff we see from LLMs starts to make a whole lot more sense. I'm talking about the famous hallucinations. A hallucination isn't the model losing its mind or having a creative moment. It's just the model following a very, very unlikely path down its probability tree. That sampling process we talked about allows it to pick a token that has a tiny, tiny chance, say 0.1%. And when it does that a few times in a row, the text can suddenly veer off into some really strange, totally fabricated territory. It's a feature of the system, not a bug. And this brings us all the way back to the original question. After seeing the mechanics, right? The tokens, the probabilities, the sampling, the chess player calculations, can we really call any of this thinking? AI pioneer Andrej Karpathy just nails it with this quote. These models aren't minds. They are incredibly powerful simulators. They have learned the statistical patterns of human language so well that they can generate text that is often totally indistinguishable from something a person would write. It is an amazing simulation, but it's not sentience.
So let's try to put all this together. The most important thing here is to have the right mental model for what these things are. We're not dealing with some new form of consciousness. We're dealing with an incredibly powerful simulator. They are tools, not teammates.
So what's the bottom line here? What do you need to remember? LLMs are just brilliant statistical simulators, not thinkers. They build their responses one token at a time by sampling from a list of probabilities. Their so-called intelligence is really an illusion born from massive scale calculation, not consciousness. And that's exactly why they will always be powerful tools that require our guidance, our context, and our critical thinking to be used well. And that leaves us with one final, kind of mind-bending question to chew on. As these simulations get better and better, we have to ask ourselves, if you genuinely cannot tell the difference between a simulated mind and a real one,